before we start the lesson today, are there any questions on the homework? Any questions on any of the homework assignments so far? The assignment today is kind of nice. The first thing we're looking at is the factor theorem. Now there's several parts to this. You don't have to write all this down. Don't write all this down. So when we talk about the factor theorem, when dividing the polynomials in previous sections, the examples had non-zero remainder. So the remainder was something other than 0. Suppose the remainder is 0 when you divide a polynomial. So we end up getting, messing everything up. So suppose we get a non-zero, or we get a 0 remainder. So that means we get whatever the quotient is, q of k, times our remainder, which is just q sub k, is the quotient. Therefore, whatever we divided the polynomial by times what we got is going to give us the following, or give us the original polynomial. So really what this means, the factor theorem is telling us, is whenever a polynomial f of x has a factor x minus h, it has a factor x minus k, if and only if f of k equals 0. So if we evaluate it for a certain number, or we divide the polynomial by a different polynomial, this term here, and we get a remainder of 0, it means it's a factor. It divides into it evenly, such that we can say what we divided it by times what we ended up getting left over to get back to the original polynomial. So if we divide and get 0, it means whatever we were dividing the polynomial by is a factor of it. So determine whether x minus 2 is a factor of x squared plus 2x minus 4. So what we can do is our synthetic division, because if we divide it with synthetic division or long division, either one, and we get a remainder of 0, it means it's a factor. Well, to do synthetic division, the first thing we're going to do is set x minus 2 equal to 0 and solve for x. So the first thing we can do here is add 2 to both sides, telling us x is 2. So the number that goes in the cubbyhole is 2. Now the numbers that go across the top are our coefficients. So we would have 1 for x squared, 2 for x, and then negative 4. And the next thing we would do is bring down the 1. Any questions on how we set this up? Now we do multiplication, so we do 2 times 1, which is 2 plus 2 is. Then we multiply again, 2 times 4 is. Negative 4 plus 8 is. Is 4. So here our remainder is. So is x minus 2 a factor? No. Because for it to be a factor, the remainder had to be what? 0. Is it the remainder of 0? Then it is a factor. If it's not 0, then it's not a factor. Questions on this here? Let's look at the next one. Determine whether x plus 5 is a factor of the polynomial 3x to the 4th plus 15x cubed minus x squared plus 25. So we can do it with synthetic division. Now we need to find the value that goes in the cubbyhole, so we can set it up as x plus 5 equals 0. And we would. So you'll need to go at, yeah, one of the pages is out of order. Yep, we're right here.
Oh.
Any questions on how we found the number that goes in the cubbyhole? Now the numbers that go across the top are going to be what? 3, 3. 3 for x to the fourth, 15 for our x to the third. Negative 1 for x squared. Because we don't have an x to the first, or x, so we need to put 0 in its place. And then we would do 25. Because we need a number for x to the fourth, x to the third, x squared. We need one for x in 25. We need one in each place. So whatever the degree is for the synthetic division, we'll have one more term than the degree. Since the degree is 4, we need 5 terms. Because we'll have 1, 2, 3, 4, 5. The number of terms or number of numbers we have for synthetic division is always one more than the degree. And the first thing we do is bring down the 3. Negative 5 times 3 is negative 15. 15 plus negative 15 is 0. Negative 5 times 0. Negative 1 plus 0. Negative 5 times negative 1. 0 plus 5. 5 times negative 5. 25 plus negative 25 is x plus 5 a factor. It is a factor, yes. Now the polynomial that we have, so we have 5, negative 1 would have x, 0 would have x squared, and 3 would have x cubed. So we have x cubed minus x plus 5 is what we have left over, yes? And what it means with it being a factor is if we multiply this by x plus 5, we get back to our original polynomial. Because they're factors, they multiply together to get back with what we started. And this is, I mean, we didn't write this out, but we did say that this was our solution. But these two multiplied together to get back to where we started. So if we said something simple, let's say 21 divided by 4, not 4, let's do, instead of 21, let's say 28. So if we did this division, well, 7 times 24 is 28, 0, we have a remainder of 0, yes? So we're saying that 4 times 7 are our factors, and they'll multiply together to get back where we started. The same thing's true with polynomials. So these here are our factors. Questions on this here? Let's look at the next one. X squared plus 6x minus 12. So we need to find the number that goes in the cubby hole. So here we would add 3 to both sides, telling us x is equal to 3. So the number that goes across the top would be what? So we have x squared, yes? So x squared, x negative 12. Well, what is the degree of the polynomial that we have here? 2, yes? So we need one more than the degree, which would be 3 terms. 1, 6, negative 12, we have them all. And another way you can think of it is, so our exponent attached to the the variable attached to the biggest exponent is x squared, yes? So 1 less than it would be x to the first, or just x, and then without 1. So we have all 3. And you could do that as you're writing them down. So x squared, x, constant. Counting them down to make sure that we have them all. Next thing we can do is drop the first term. And we do 3 times 1, which is, add straight down, 3 plus 6 is, 3 times 9 is, add straight down, we get, so is x minus 3 a factor? No, not a factor because the remainder is not 0. Questions on any of this here? Questions on anything we've done so far? Okay, let's look at the next one. Determine whether 3 is a factor of this here. Hold on. So we can start off with x plus 3 is equal to 0. And the next thing we would do is subtract 3 from both sides, telling us x is equal to -3. So the numbers going across the top, we'll have 2 for x to the 4th. Then we'll have 10 for x to the 3rd. We have 11 for x squared, then -1 for x and 6. Since the degree is 4, we need 5 terms. We have 5 terms, so they're all here. And the first thing we can do is bring down the 2. And then we do what? -3 times 2 is -6. 10 plus -6 is 4. -3 times 4 is -12. 11 plus -12 is -1. -3 times -1 is +3. 3 plus -1 is 2. And -3 times 2 is -6. And lastly, 6 plus -6 is, so is this a factor? Yes. And our final polynomial, what we can say is x plus 3 times 2 is our constant term. -1 would have x, 4 would have x squared, and 2 would have x to the 3rd. So we have 2x to the 3rd plus 4x squared minus x plus 2. Questions on any of this here? Questions on anything we've done so far? Most likely no, because they're just determining whether or not it is. Because this is kind of good to just keep in mind, this is what we are saying, that they multiply together to get back to what we started. Do we have any other questions on these here? Do you feel comfortable with these? Okay. I'm going to go to the one after it. Show that x plus 3 is a factor. Then factor completely. So when we factor completely, we want the degree of each one in the set of parentheses to be 1. We want to factor it down as far as it'll go. So the first thing we can do is show that this is a factor. So if we do this here, well, the first thing we can do is subtract 3 from both sides and say x is -3. Now, our numbers across the top, for x to the 4th, we would have 1. For x cubed, we would have 3. For x squared, we would have, for x to the 1st, we have -1. And for our constant term, we have, now we bring down the 1. -3 times 1 is -3. Yep. 3 plus -3 is 0. -3 times 0 is 0 plus 0 is -3 times 0 is -1 plus 0. -1. -3 times -1 is, and -3 plus 3 is 0. So it is a factor, yes? Well, we knew that from the get-go. Because what were the instructions? Show that x plus 3 is a factor. So they're essentially telling us it is. Now, part of the reason we're doing this and doing the first part of the factoring, well, do we have a good way to factor x to the fourth plus 3x cubed minus x minus 3? I mean, no and yes at the same time, because we did go over weight yesterday, we could have done this. Now, if we look at what we have left, so if we look at this here, I put the variables back in. So this was our remainder. -1 is our constant term. 0 is x, this 0 is x squared, and this one is x to the third, yes? So what we have is x to the third minus 1. Well, whenever we have two numbers being added or subtracted, well, if they're perfect cubes, we can factor it. Or if we have the difference of perfect cubes, we can factor that. Can we take the cubed root of x to the third? What's the cubed root of x to the third? X. Whenever the exponent and the root are the same, they simplify each other out. Now the other question is can we take the cubed root of 1? Is there a number when multiplied by itself 3 times that gives us 1? Really, no matter how many times we multiply 1 by itself, it's still just 1. So what that's telling us is that this here is the difference of perfect cubes. So, well, deciding. So the factoring we went over yesterday, our sum and difference of perfect cubes, we can set it up from there. So we can do the signs first. The signs are going to be the same, opposite, always end on a positive note. So our starting is what? Minus. So the same would be minus. Opposite would be plus. Always end on a positive note. Now, I didn't say this yesterday, but factoring these sum and difference of perfect cubes has shown up on the ACT before. Because they've asked you to find the factors of this here or factor the following polynomial, and they'll sometimes give you this here. One of the things I would say is just remembering the sign, same, difference, always end on a positive note, will eliminate some. Because you can go through and look at the factors and see which one of the signs do match. The ones that don't, we can cancel out. Now, the values of a and b that go in here, well, a is going to be what? X. B is going to be 1. So we know that we'll have x minus 1 in the first set of parentheses, yes? And that can help you eliminate some, because if it doesn't have x minus 1 in the smaller parentheses, it's not the correct one. Makes sense so far? Now for the bigger set of parentheses, well, here we have a squared. The middle one we have a to the first, and the last one we have a to the 0. So we'd have x squared, x to the first, x to the 0, which is just 1. Our b's in the first one, we'd have b to the 0, so 1 to the 0, which is just 1. So it doesn't really need the b there. In the middle one, we'd have 1 to the first. And lastly, we would have 1 squared. So when we simplify this here, we get x minus 1 times x squared, because that's just x squared. 1 times x is going to be x, and 1 squared is 1. Questions on this here so far? So we wanted it completely factored, yes? There's one other factor we need. What did we prove was a factor? Our x plus 3, yes? So that there is it factored completely. Now the question might be with the x squared plus x plus 1, that will never factor. The quadratic part of the sum or difference of perfect cubes will never factor. That is as simplified as it gets. Questions on this here? Yes.
Is that -1 because that's a constant term? Okay, so we just bring that out.
Mm-hmm. Yep, the signs in front of it come with it. So if there's not a sign in front of it, it's understood to be positive. Any other questions? We're going to look at another one. Show that x minus 2 is a factor of this here.
So it's kind of like a mix of what we did 2 days ago.
Mm-hmm.
X plus 2.
Yes. Really, we can do this completely with what we did yesterday. And I'll show you that here. Well, we can show you, I can show that on the last one. Here, if I look at this here, I said we could do grouping if we have an even amount, yes? It might not always work with an even amount, but sometimes it might. Because if I look at these first two terms, what is their greatest common factor? X to the third, yes? And if I factor x to the third out of x to the fourth, I'm left with just a single x, yes? Plus, if I factor an x to the third out of 3x to the third, we're left with 3. That is one of our factors, isn't it? Because they told us x plus 3. Let's look at the other one, negative x minus 3. What's the greatest common factor? Negative what? Because if I factor a negative 1 out of negative x, I'm left with positive x. If I factor a negative 1 out of negative 3, I'm left with plus 3, yes? So grouping, both of these now have an x plus 3 in common, so we can factor it out, which leaves us with what? X cubed minus 1, which then we can take it from there to say that this is x minus 1 times x squared plus x, essentially what we did. Different ways to get there. Now, the main reason we're doing it this way is so that we can see that division does give us factors and we can work from there. So if we look at this one, well, cubbyhole line. So inside the cubbyhole, we'll do x minus 2 equals 0. So we would add 2, telling us x is 2. Numbers across the top, we would have 1 for x to the fourth, negative 2 for x to the third. X squared would be 0. X would be 1, and then we would have negative 2. Questions on this here? So we do the multiplication again. 2 times 1 is 2. Negative 2 plus 2 is 2 times 0 is 0. 0 plus 0 is 0. 2 times 0 is 0. 1 plus 0 is 1. And lastly, 2 times 1 is 2. And negative 2 plus 2 is 0. Now, if we plug the variables back in, this would be our remainder. The one next to it is our term without a variable. We would have x, x squared, and x cubed, giving us x cubed plus 1. Can we classify this as the sum or difference of perfect cubes? Yeah. I mean, the one before it, we had x cubed and 1, yes? The only difference is the sign in the middle, so we can still do it. Because again, the cubed root of x to the third is still just x. The cubed root of 1 is still 1. Our signs, almost. if we look at the sign, so again, how do the signs go? Same, opposite, always end on a positive note. So I know that this one down here is going to be plus. But the same, so what did we start out with this time? Plus, so the same would be plus, opposite of plus would be negative. So it's almost the exact same, except the signs are different. For our variables, our a value, a this time is still x, b is still 1. So this time our first parentheses is x plus 1, where the last one it was x minus 1. Then here we would have a squared, so it's x squared. Then we'd have x to the first, x to the 0. With 1, so we'd have 1, 1 to the first, and 1 squared. Which really just factors to x plus 1 times x squared minus x plus 1. Or x minus 2 that we started with. Any questions on any of this here? Now, when we solved by factoring, because last chapter when we solved by factoring, if we were solving this and this was equal to 0, we said any two or more things multiplied together to equal 0 means one of them must be 0, yes? Because when we solve for graphing, we're trying to see where it crosses the x-axis, where the value equals 0, yes? So the factors are a solution, which also means, and we'll get there, that if the remainder is 0, this number has to be a solution. We'll look at one more. That's fine. This is the last one we're going to look at here. Show that x minus 6 is a factor of this here, and then factor completely. I have a feeling most of y'all have gotten comfortable finding the number that goes in the cubby hole. Now the numbers across the top, so we have x to the third, so that's going to be 1 for x to the third. X squared is -5. X is -6. And we have all of our numbers, yes? We need one more, which is 0. Because the degree is 3, so we need 4. Because we have x to the third, x squared, x. We are just missing our constant term. Next thing we can do is bring down the 1 and start this here. So 6 times 1 is 6. -5 plus 6 is 6 times 1 is 6, yes? -6 plus 6 is 0. 6 times 0 is, and 0 plus 0 is 0. So we showed that this is a factor, yes? Now let's plug the variables back in to see what we've got. So this is our remainder. The 0 next to it is our term without x. The 1 next to it is our term with x, and this is our term with x squared. So what we're left with is x squared plus x, yes? This is a little bit nicer. Even though there's not a number, because if there had been a number after the x, we could try to factor with 2 sets of parentheses. Go back to how we factored quadratics. But before we did any factoring, what was the first thing we always looked for? A like term, a greatest common factor, yes? Is there a greatest common factor between x squared and x? So I could factor that out, yes? If I factor an x out of x squared, I'm left with x. So we're really dividing it. So x squared divided by x is going to be x. What's x divided by x? Anytime something factors out completely, it's going to be 1. The only way we can get 0 is with subtraction. Subtraction is the only way we can get to 0. With division, we have to have some term there because we have to be able to multiply it back to get back to x. Does that make sense? But we did have one other factor, which was our x minus 6 that we started with. And that's it. Questions on any of this here? Not too bad so far? Okay. Now we said x was a factor, yes? I'm going to show you this here. You don't have to write this out. But if we look at the original problem, is there still a greatest common factor of x between these three terms here? Well, yes, I could factor that out, which would leave me with x squared minus 5x minus 6. Now I can still do this here because we said 6 was the number that went in the cubbyhole, yes? So across the top we would have 1 for x squared, negative 5 for x, and negative 6. 1 times 6 is 6. Negative 5 plus 6 is 1. 6 times 1 is, which gives me 0. If we plug the variables back in, this is our remainder, our term without x, our term with x, so we have x plus 1. We have the other factor of x, and that's the same thing we got. Yeah. If it's a factor at one point, it's going to be a factor at all points. That's just showing you that it still works no matter where we do it along the line. That's it. Because what we're leading up to is solving. What we're leading up to is solving. Because as you notice with all of these here, when we divide, we decrease the degree by 1 each time, which helps us find the solutions. Because if we can get these down to a degree 2, we can use the quadratic formula to finish solving from there.